Today we're going to look at our final reaction type, the double replacement reaction. So this reaction occurs between two ionic compounds that are in solution. So we will be able to identify this reaction by looking at the reactants and seeing what they are. And if we have two ionic compounds, then we know that it's going to be a double replacement reaction. Now, normally these reactants are in solution, and the reason why they're in solution is that, remember, when we put ionic compounds in solution, those ionic compounds will dissociate. So we'll have the cation floating around and the anion floating around. And so when we mix them, right, we're going to be able for those things to trade partners because they're already separated like a big square dance, right? So we can have this where A being our cation, we add it, we'll be able to couple up with D in the other solution because, again, they're dissociated and they can trade partners. And then our cation C can then come back and couple up with B. Now, the big thing to remember when we're doing this is, number one, remember that cations are always written first in our ionic compounds. And number two, we have to pay attention to the charges. So when we're writing these out, we can't just mash them together. We have to pay attention to the charges and how they're actually coming together and write that new compound correctly. And then after we write it correctly, we can go back and balance it. Now, in order for a double replacement reaction to happen, and if we mix these two solutions, how can we tell that there's actually going to be a reaction there? Well, the big thing is they're either going to result in the formation of a precipitate, and remember that's one of our indications of whether or not a reaction has occurred, or we're going to see a gas being formed. Okay, a great example of this would be when we take a solution of potassium nitrate and lead 2 nitrate and potassium iodide, and we mix them together, right? So since they're in solutions, those ions are already separated, and if we look, we're going to get a double replacement reaction here and here. And so, but the thing about this is that when lead and iodine come together, that attraction between those ions is so strong that this forms our precipitate. And so it does not dissolve in water. We have that new chemical compound that has new properties, and we see that. And we've already taken a look at this, but let's take a look again because I think it's worthwhile. Okay, and so here we have our two solutions, and potassium iodide and lead 2 nitrate. We add those two solutions that are originally clear, and boom, and lo and behold, when they come together, now the lead ion couples up with the iodide ion that's in solution, and they form this insoluble solid lead 2 iodide. Okay, and so we get that pretty yellow color. All right. Now, if I'm looking at this and I'm looking at these two things and I say, okay, Lambert, how do I know that this is my precipitate, that lovely yellow thing that we saw, as opposed to that one? How do I know that? Well, the good thing for us is that there have been lots of experiments done on lots of different solids, especially ionic solids. And so we have some pretty good data on what ionic solids dissolve pretty easily in water and what ionic solids do not. And based on that, we have come up with something known as the solubility rules. The solubility rules, for us, we're going to keep them simple. There's going to be 3 of them, right? And so based on all those experiments, what we know is that if something contains an alkali metal ion or an ammonium ion, so the cation is an alkali metal or the ammonium ion, all right? No matter what the ionic compound is, that substance will dissolve with water. So if that is present and we have that as a product, we know that that thing will not be our precipitate. right? So if we go back up here and we're looking and we produce these two things and we see, oh, well, this one over here contains the potassium ion, which is an alkali metal, right? Well, if it has an alkali metal, then we know that it will dissolve in water. So if we see a precipitate, then by process of elimination, it must be the other substance. That's about as easy as it can get, all right? We can also look for anions, and two anions are nitrate and acetate. If those anions are there, that substance will dissolve in water. And so again, right, we go back up here, and this is a double whammy because this also contains nitrate. And so because it contains nitrate, we know it's going to dissolve in water, so the other substance must be my precipitate. And then finally, the last one is a little bit tricky, but we need to point it out, right? Most of the time, and I say most of the time, right, those things that contain halogens will dissolve in water. There are some exceptions to this, as if the cation is a silver, mercury, or lead. And when this cation is silver, mercury, or lead, for example, we have AgCl or PbI2 like we saw in the video, those guys have a strong enough attractions where they actually will form a precipitate because they won't dissociate very easily in water. So these are very important rules to look at when we want to know what substance is going to form that precipitate. Okay? Now, we can also form a gas, and there are many double replacement reactions that form gases, but we're not going to get into them all. There is one example that I really want you to know because it's really common, and you guys have probably already done it through middle school and whatnot, and that is the formation of carbon dioxide. And so for this particular reaction, we're going to look at a very specific instance. And so if we have basically an ionic compound, and that ionic compound contains the carbonate anion. So we have the carbonate anion. I still can't spell. Carbonate anion, or the hydrogen carbonate anion. Right? And so it doesn't matter what the cation is. Cation can be anything. Doesn't matter. But we're looking at specifically that anion. And if we take that anion and we react it with an acid, again, the acid part, right, anion doesn't matter particularly. What we're concerned about is this. Because here, when we're going to go over here, we're going to get our double replacement. What we're going to look at specifically is this hydrogen coupling up with the carbonate or the hydrogen carbonate, right? And we may look at that example and say, oh, well, we do that. That's going to be easy. We're going to form H2CO3 when that happens. Now, the problem is this is unstable when this forms. And so since it's unstable, it immediately decomposes into carbon dioxide and water. Okay, and so obviously when we have that, we're going to see bubbles because of the carbon dioxide. Now, anytime you've ever mixed baking soda or baking powder and vinegar at home, right, you've done this reaction. This is what you see. And so in this case here, again, right, we have our sodium carbonate. We react with hydrochloric acid. And as a result, we're still going to get sodium chloride as in solution, but we're going to form carbon dioxide and water, and we're going to see lots of bubbles. Okay, and so again, remember, this looks like it should form this, but that decomposes. So this should be your final product. I don't want to see this in your answer. Okay, and again, you guys have all seen this. So let's take a look about what this looks like. And it's really pretty simple, right? Lovely double replacement reaction. And here is our sodium carbonate, maybe even sodium hydrogen carbonate, sodium hydrogen carbonate in this case. And we add some hydrochloric acid to it, and immediately you see it start to bubble, right? Those bubbles in this case are that CO2 gas that's being released, okay? And so we're releasing that CO2 and we're forming water in addition to NaCl that's being left around in the solution. So basically we're making salt water and we're letting that carbon dioxide go away. Okay, so this is a double replacement reaction, can get pretty exciting. Make sure you look over and review those solubility rules. And so for today, make sure you're answering that assessment, okay? Let me know if you have any questions. I hope you guys are doing well. Peace, love, happiness. Thanks for playing.